Okay, so this is graph theory. To begin with, I want you to pause this video and watch. This is 3.14. I'd like you to watch how the Konigsberg Bridge problem changed mathematics. Okay, so pause this video, watch that from Cognity. Okay, now that you've watched that, it's kind of an interesting little video. Um, the concept, while searching for real-world solutions to real-world problems, it is often helpful to build a model that only includes the most important information. And so that's what Euler did with graph theory. So definitions, we're going to have a lot of definitions here. Um, a graph is a figure that contains vertices and edges. Vertices are points, such as, A, B, E. Edges edges are these lines connecting them. Doesn't necessarily mean they go there, it just is a connection. So you'll see all kinds of them. You might have streets, and you can put the edges so it looks like where the streets go, but you don't have to. It simply means a connection. The length of the edge does not necessarily mean anything. A couple other terms. The order of a graph, written looks like absolute value of V, is defined as the number of vertices. The size is the number of edges. Okay? Important terms to know. Most of graph theory is knowing what it's asking. State the order and the size of this graph. Okay, the order, 4 vertices, so the order's 4. The size, 1, 2, 3, 4, 5 edges. Order's 4, size is 5. Okay. In graph theory, when two vertices are connected by an edge, they are called adjacent vertices. Similar, two edges that share a common vertex are called adjacent edges. Okay, again, terminology. List all the edges that are adjacent to AB. So adjacent edges share a vertex. AE is one. AD is one. AC is another one. Those are the three at vertex A. At vertex B, there's BE, there's BD, and there's BC. Some of this intro stuff, pretty darn easy. So we have all 6 of those being adjacent. Important, the degree of a vertex, more terminology, is the number of edges that connect at the vertex. Find the value of degree A. The degree of vertex A is 2. It's AB and BD. And this activity. Consider the two graphs shown in the figure. Let the graph on the left be the graph G and the graph on the right be H. I'm going to say top and bottom. Compare the two graphs, measure the following, the order. So go ahead and do that. And then we are done with this section. When drawing a graph, the actual positions of vertices and lengths of edges are not important. Rather, it is the connections between the vertices that are crucial. Okay, on to the next section. Simple graphs. Consider two graphs that are known here. Okay? The one on the right is more complicated. It has more edges. A simple graph is one that does not contain loops or multiple edges. A simple graph is also unweighted and undirected. We'll talk about what that means in a second. But loops. Here we've got a loop, maybe. A loop right there. I also have multiple edges there connecting the same two vertices. So the one on the right there is not simple, the one on the left is. Complete graphs. A complete graph, Kn, is a simple graph such that each of its vertices is incident to every other vertice. Okay. All of them are simple graphs. Notice K sub tells you how many vertices it has. Okay. K sub 1 is just a single vertex. It's a simple graph, so it can't have a loop, so it has no edges. K2 has just one or two vertices and one edge connecting them. K3 is triangle, K4. Notice how many more edges K4 has, and it gets much more complicated when you get beyond K4 because you must connect all the edges. Exam tip. Recall the activity 3.4.1. The actual positions of the vertices is not important. Okay. So here we've got this. Five, copy the five vertices, and it asks you to draw them. You should end up with something that looks like, see if it finds me the right spot. No, it didn't. That. And again, the locations doesn't matter. It's all about the connections. So the total number of edges in a complete graph is given by this formula. So if it's a complete graph of size 6, total number of edges is 6 times 5 divided by 2. You could try that. We saw the 5 one. 5 times 4 divided by 2 should have been 10. That one's 15. So that little formula there is useful and helpful. Make sure to get it in your notes. Okay, so far graph theory should be feeling pretty easy. Weighted and directed graphs. Okay, we see this very complicated graph here. The illustration above is a partial map for the subway network in Tokyo, Japan. Imagine you are currently at Ibukuro Station, vertex I, and you want to make it to Higanibusha Station, vertex H. So I to H. Which combination of trains could you use to get there? And then which combination is the quickest? This is where a weighted graph comes in. A weighted graph has values on the edges, like is shown here. IS is 5, IL is 9. What those weights mean depends on the graph and depends on how it's defined. Okay. That could be how much it costs, it could be how long it takes, it could be how many miles it is. Okay, but now we have all these edges have a value, so that is a weighted graph. So it says choose the quickest route to get to H. I could go IS and then SH, that's 22. I could go IS, LK, KH, that's 20. Could go IL, LH, NH, that's 21. So it's IL, LK, KH. You did have to check all the possibilities. Be aware the simple example demonstrates the concept of weighted graphs. Methods to find a solution are studied more in 3.16. Sometimes it's literally the best way is to just check them all. International mindedness. Google Maps. I'm sure you've used it. It's useful all over the world. It is using a combination of graph theory and some other things to do that. The Street View functionality is also interesting. This information details countries where Street View is available and those where it is not. There are different factors in countries that should be considered when determining whether to allow Street View functionality. So not every place has it, but a lot do. Directed graphs. Directed graphs, you can only go one way. It's kind of like a one-way street. So directed graph is a graph whose edges have a specific direction. Okay, if they don't, here's a directed graph here. Notice that FG does not have an arrow on it. That means effectively FG goes both ways. Okay, so important. The in degree of a vertex is equal to the number of adjacent edges that have a direction into the vertex. The out degree is the number of adjacent edges that have an out, that go out of that vertex. Write down the in degree and the out degree for vertex E. The in degree of E is 1. There's only 1 going in. That one should not be in parentheses, it should be an absolute value. And the out degree of E equals 2. There's EF and ED. Okay, we're up to the last graph. Subgraphs. A graph is a subgraph if its edges and vertices are contained within another graph. If any edge has a weight or direction, they must also match. So all of these shown are subgraphs. Nope, nope, nope. Um, just the middle one is a subgraph. This one here on the left fails to have weight. Not make it so big, not cover the original. This one fails to have the weight or the direction that the original has. This one here is in the wrong direction. This one, um, if the edges and vertices are contained within, if any edge has a weight or direction, those must also match. So I think the middle one still counts, even though it's missing an edge. All three graphs have vertices and edges that are in the original graph. However, as you can see, one of the graphs has no directed edges, and in another one, the edges are directed in the opposite direction. For a graph to be a subgraph, the direction and edges must match the direction of edges of the original graph. The only graph that meets the requirements is the middle. Even though it's missing one of those edges that is there, it's still considered a subgraph because everything that's there is the same. Um, Exam tip. Recall the actual positions of the vertices do not need to be the same. This also applies to subgraphs. So E goes out to D and F, that's correct, and D goes to F. This one right here is a subgraph, even though it doesn't look the same as what the DEF in the original. Okay? That's introduction to graph theory. Hopefully this doesn't seem too bad.